Okay, in this lecture, I want to go over the basics of Scala. I'm not going to go over everything because at this point in your CS career, you should be comfortable in learning a new language, right? Being able to look online for API documentation, figure out how do I get the length function of a list, those sorts of things. But I do want to go over sort of the little idiosyncrasies of Scala that we're going to be using throughout this course. So the first thing is there's two types of variables. There's vals and vars. And vals are immutable. That means that we can't change their value, while vars are mutable. Right, so like in C or C++, a val would be a const definition, while a var is your normal variable. Right, so in both of these cases, when I run it, they're both integers. In Scala, we do a little colon and then the int that gives us the type information for what x will be. We don't actually have to do that in this case because Scala has pretty good type inference. It can guess what you mean. But it's always useful to keep writing all of the types down just for your own sake and for clarity. So yeah, we can define both x and y to be ints that are equal to 10. And if we try to redefine x, we can't, right? And that's because a val is completely immutable. It's just a name to some value, right? Well, a var is our typical idea of a variable. And in this class, we'll actually be programming pretty much only with vals. We'll have a few assignments where you're not even allowed to use vars. And that's because in a sort of a functional approach, we don't really want to be dealing with mutability of our variables. We want to think about it just as data, and we make new data and return that new data. So yeah, we can't assign anything to x again. X is just solidly set as 10, but we can update y if we want, right? So we could update y to 12, we can add 1 to y and then print it out and we get 13. So yeah, that's sort of the difference between vals and vars. And we can, chain a bunch of vals together. Vals are just a way to give a name to a value in our program, right? So oftentimes we'll have complex values and we'll just want to sort of make it more succinct by giving it a name. And that's the goal of vals in the language. Okay, let's look at a function definition. So to do functions, right, we define them with this def keyword. And then all functions and actually all variable names should be lowercase. Uppercase names, those are for types. So you always want to start your functions or variables or vals with a lowercase letter. So we have here def my first function. It takes an x as an int and returns an int, right? This is just like in C where we put an int at the very beginning, right, or a void or something like that, to say what the type of the return is. In Scala, we put the return value after the name. And we say equals, and then we make a big curly brace. And the curly brace is the limits of the expression of the function. An important thing to note is all of the parameters need to be typed. The return value doesn't actually need to be here if we don't want. We can delete that, and this will still compile. Oh yeah, it fails to compile for a different reason. But in general, Scala has good type inference, so we can ignore the return type. But we always need the parameters type. So let's look at why this failed, right? We see reassignment to val, y equals y minus 1. Well, what's this function doing first? Right, my first function, it takes in an x, which is an int. It returns an int. And while, we don't have a y, right? We have x's everywhere. So while x is bigger than 0, we're going to print x, and then we're going to decrement x by 1. And then we're going to return 0 at the bottom here. And this still fails. Okay, why? Well, reassignment to val. And this is sort of a little hint here. All the parameters in functions right here are vals, right? So we don't ever pass variables into a function. We pass vals in. And we'll see how this makes working functionally very easy. But it's a first little thing to get used to. So we can't actually do this because we can't just decrement x, right? So how could we fix this? Well, the easy way to fix this is to make a separate var. Let's say, let's call it y, right? And then do all of our decrementation and everything with y. And there we go. We get it printing out every number from 10 down to 0. Now, a couple little details here. This Scala is built off of Java. It actually compiles down to Java bytecode, so it runs on top of the JVM, right? The JVM takes Java bytecode, which is not quite as low level as assembly, and then interprets that into machine code. And Scala basically takes the Scala program and turns it into JVM bytecode. So that means that you can play with Scala and use Scala with Java at the same time if you want. So a lot of the Java syntax is sort of built in here, but Scala is a little looser frequently with it. So for instance, the brackets are all out of Java, the semicolons as well, but you don't actually need semicolons unless you're for it to work, right? Unless you're doing it on the same line, right? We could do this, and then we need a semicolon to separate out the fact that those are two separate expressions. But in general, we don't need a semicolon anywhere. The other thing that we don't need, if you notice, I didn't type in return 0 here. I just had 0. And it works with both with return and also without return. Now in Scala, return is sort of used for when I want to escape halfway through a block of code. And we're not actually going to be doing that much. So throughout this program, I'm going to recommend that you do not use return statements. The way this works is that everything that's in a curly brace block, that's an expression, and whatever the very last thing in the expression evaluates to is what that block returns. So in this case, this whole block here, this while block, or this full function block, it runs through this while loop, and then it sees a 0, and so the last thing it returns is that 0. And you'll get very comfortable doing this as we go through the course. Basically, anything at the last line of your code is what is always going to be returned. It could be a function call, then whatever that function call returns is going to be returned back up, or it could just be a statement like this. So yeah, we can also define this recursively, right? So here we had this while loop. We're going to actually be avoiding for and while loops in this class as well. It's useful to sort of know how they're built up, but we'll have assignments where you're forbidden to use either for or while loops. And instead we're going to do everything recursively. Right, so here's the recursive version of it. What does it do? It's a function, my first function rec. It takes in an x, that's an int, returns an int. If x is less than 0, then we return 0. This is the base case. Else we're going to print a line, and then we're just going to call the recursive function on x minus 1. Right, so instead of counting down with immutable, we just basically rewrite, or we pass on a new value, right? X minus 1 is just a value that we pass on to the next iteration of this function. So this is an easy way to sort of replace a while loop with a recursive function, right? Basically, the if is the base statement, right? While y is greater than or equal to 0, so if x is less than 0, right? Else is the body of the while loop with the recursive call as the sort of update statement. And again, there is no return statements here, right? We just see that if x is less than 0, then we return 0, so that's just 0. Otherwise, the else part, it's whatever the last thing is in that block of text, which eventually will be whatever my first function rec of x minus 1 returns. Here's another example with a while loop, right? This is going to count how many occurrences occur in a string of a character, right? So we have stir, which is a string, ch with a character, and returns an int. So what do? We make a new counter, right? A variable. We set to 0, and it's going to be the size of the string, right? To look up these sorts of things, just look up the API for strings, and you'll see how to look up their size, how to do substrings, all of the different aspects that you might need to deal with strings. And then we have a for loop, and this is, the syntax is, I think, closest to Python, right? So here we have the iterator that we're going to do, I, and this is a little less than minus sign. That's actually a leftward pointing arrow, and the 0 until n is just like in Python the range from 0 to n. It's an iterator that says, okay, give me a list of all the numbers from 0 to n and list them off one by one and then put them into this variable I. So every time we go through the for loop, I will be updated from 0, 1, 2, 3 all the way up. And what do we do? Well, if the ith element of string, in Scala we don't use square brackets for either substrings or elements of a list. We use normal bracket or normal parentheses. So if the ith character in string is equal to ch, then we increment our count. We don't need an else statement. If we would leave it in there, it would just be returning an empty parentheses, which actually is a type in Scala. It's this type of any. So if you don't have any sort of type, it'll just be an any type, which is sort of a placeholder for it could be possibly anything. We'll talk a little bit about that near the end of the course when we talk about Scala's type system. But suffice it to say, you don't need to always have an if-else statement. You can just have an if statement. Right, so let's see if this works. Right, so we have val z is a hello world, and then we'll see how many O's show up and how many spaces show up in there. That seems to work out well, right? Okay, so let's do this recursively. How would we do this? Well, we don't want to do a counter, right? We want to do this recursively. So still we want to say, well, what do we want to say? We want to see whether or not the first element is the same character as the character we're looking for, right? And if it is, well, then we know that we've seen one and we have the rest of the string to go through, right? So we want to basically recurse on the rest of the string. So we can do this, right? So if string of the 0th element is equal to ch, then what do I want to do? I want to add 1 to whatever recursive count HMO does on, well, s dot substring starts with 1. So substring is a function that you can call an s, and we'll pull out the substring that starts with the index that you give. So strings, we start counting at 0, so saying substring of 1 gives us the everything but the first character. We'll pass in the char there. Right, else, what do we do? Well, if the first element isn't the character we're looking for, then we don't increment our count, right? So it would be something like 0 plus recursive count HMO substring character, right? And we don't even need the 0 plus if we don't want. Oh, that failed because of, this should be just s. There we go. Actually, I have a version of it down here too. So we can see if that works, and it does, as you'd sort of expect. So this is a way to basically replace a for loop, right? So we saw how to replace a while loop with recursion, and this is how we replace a for loop with recursion. Now, when we say that Scala is a functional programming language, really the key point there is that functions are first-class types. That means that we can pass functions into a function, right? So this is what we're doing with this little block of text here, function A. What does it take in as its parameters? It takes in an integer called x, and it takes in a function foo, which takes an integer to a string. Right, this is the way that we write the type annotation for a function, with the equals greater than or equal sign being an arrow that says I'm taking an int and returning a string. So foo is a placeholder, right? It's the name that we're giving for the parameter, which is going to be a function, and that function should be something that takes an int and returns a string. Function A itself returns a string. So what does it do? Well, if x is, say, less than or equal to 0, it just converts x to a string. Otherwise, it will call foo on x. Now, toString is actually a function defined in x. X is a object in because everything is also an object in this world, right? So in this case, x is an int, but it's easy to turn it into a string. It doesn't actually change x itself. It returns a string form of x, right? X is a val. And so we're not actually modifying x, we are saying, hey, can you give me a version of x that's in a string format? And that's what it's doing here. And so what we've done is we made a function that takes in a number and a function. So let's make a couple functions that are of the right type, right? They take in an int and return a string, and both of these do that. So this int to string fancy converter, it takes in an x as an int, returns a string, and all it does is writes down natural number colon space and then plus x. Scala is smart enough, it's overloaded the plus operator so that you can add strings to numbers, and all it does is turn the number into a string and concatenates the strings. Right? We can do it in an alternative form, right? That's what alt converter does, where we call the toString function on x. That gives us a string, and then we add them together with a plus, right? We can take two strings and just add them using plus in a sort of a natural way. And now we can pass both of those functions individually into our function a and see what happens. All right, so we see when we pass in 100 and into string fancy converter, we get natural number 100. When we pass in a negative number, that calls this if statement, right? So we don't actually call what is called foo here, right? So we just get minus 20. And then if we pass in 120, we get the alt converter text attached to here. One thing to sort of point out is that inside of function A, whatever we pass here is renamed foo, right? This is part of what's called the scope, right? Where whatever we've given, we might have named it alt converter down here, but once we pass it in, function A sees it as the name foo. And so it just operates locally with foo inside of its body. So we're going to be doing this a lot, where we end up passing functions into functions. We can even have functions as return values if you want. So functions are just a first class type of object in this programming language. Another useful thing is tuples, right? So tuples you might be familiar with from Python, and they're sort of immutable lists. They're very useful for if you have a function, you need to pass back more than one thing. Because functions are only allowed to pass back one object, we can pass back a tuple instead. Right, so if I need to pass back multiple things, I just pass it back. I don't have to mention what is the types of this, because it does the type inference for us. We always can, though. We could say that this is int string, and Scala will be just as happy with us doing that as leaving it out. To access the elements of the tuple, we can use this shortcut of underscore 1, 2, 3, 4. I think all the way up to 15 is the limit. You don't really want to be using tuples for more than, say, 4 elements anyway. So that's just a thing to watch out for. Another thing is that in the tuple world, there's no underscore 0. We start counting at 1. So the first element of x is 1, right? And so underscore 1 returns 1 here. So a couple little details to watch out for. Right, so yeah, we have a variety of built-in types, right? Ints, characters, doubles, floats, strings, all the sort of basic things. And they all have handy helper functions. This actually are all types of objects. So x.toChar will turn a integer into a character. We have bar here, it takes 2 ints and returns a string, and right, it adds the 2 integers together and then converts them to a string. Again, it doesn't change them, it just returns a string that is equivalent to x plus y, right? A new object, a new piece of data. So we're transforming, or maybe making a new something, as opposed to modifying a mutable. And parafun here, right, this is just shows that you can easily return tuples. And if we want to go through and really figure out what do the types look like in terms of the way that we want to be passing in functions, right? We see foo is type int arrow char, bar is type, it takes in a tuple, int and returns a string, and parafun takes in the tuple int string int and returns a tuple itself int string. A couple of the big data structures that we're going to be using, right? So is mostly lists and maps. That's what we're going to be dealing with. We'll see an array once. We won't really be doing anything with sets, but it's always useful to know. And again, lists and maps are immutable, so we can't actually change them. We can make them, we can ask for subsets of them or change them around, but we're always get a new object out, right? A new list out. We're not going to be changing the internals of the list. The array is a mutable list, so we can do all of the normal things that you might want to do with, just a block of memory that you have indexable access to. But we won't actually be doing that in this course very much. We're going to be dealing with these immutables. So how do we write a list? Well, this is where the square brackets come in. This tells us what is the type of the list, right? The list is going to be a list of integers, so when we define it, we say x is going to be a list, and then in brackets, square brackets, int. We'll see where this sort of syntax comes from later. We talk about generics and specifying generic types of things. But for now, just take note of the syntax that when we want to build a list of some type like int, we say list square brackets int. And then we say, well, it equals list, and then in parentheses, all of the elements of our list. So this builds, a list 1, 2, 3, 4, 5. We can do lists of strings, lists of tuples. We can look at the length function, right? X.length will give us the length of the list. We can access elements of a list using parentheses, right? No square brackets, but parentheses. Again, 0 indexed. One of the more useful ones is the head function. That pulls off the first element of a list. And the tail function, that gives us the remainder of the list. Right, so we got 1 and then everything after 1. And this is just like a linked list. In fact, Scala kind of handles it under the hood like a linked list, where it's actually easier to get the head of a list than the last element of the list. So we always sort of work from front to back, and often we will be pulling off the first element of the list using head, and then recursing onto the tail of a list. Obviously, there's other useful ones like reverse, gives us the reverse of the list. If we want to append to the front of the list, right, just like I mentioned, sort of in a linked list style setup, so getting the head is easier, and also appending onto the front is easier than appending onto the back, which is a little opposite of how, say, Python works. But to append something onto the front of the list, we use these double colons, which is called the cons operator. It comes from Lisp originally. And what it does is says, I want to put what into the front of the list y, and just sort of put them together. If we have two lists that we want to join together, then we can use the ++ operator in order to combine those two together. If you want to, say, add an element onto the end of a list, right, we could say do this, right? So we can't just add the element what to the end of the list, but we can wrap it in a list itself and then concatenate those two lists together. And that will work just as well. Just to look at for loops, right? So our list here, this is going to be what we pull from, and then we say for basically every element in the list, one by one, it pulls off the element starting at the first one and walking our way down and does whatever is on the inside of this. Right, so that's sort of the same as before, except instead of a range, we can use a list, and we just walk through the list. Alternatively, we could do a for each. And we'll see how this works a little bit more later when we talk about functors. The idea here is that on Y3, for each element of that, I want to apply this function to that element. And this is what's called an anonymous function. We'll get into greater detail of that later. But it says, for each element, right, let's call that ELT, and then what do I want to do with it? I want to run this code on it. right? So it's really the same structure, just a sort of a shortened way to do it in a more functorial notation. Just like Python's dictionaries, we have a map statement, right, or a map data structure, and it ties key value pairs together. And this is how you do the definition, right? So we have map, and then in parentheses we have the key, an arrow, and then the data. And it builds up our map as is. You can see it even does the type inference here, where it figured out that it is a map that goes from ints to strings. We'd have another map here that goes from string to string. There's the useful contains statement, which just checks, does M2 contain the key hell, right? If so, let's print that out. You can see, does it contain 15? It does not, so if we try to print that, we get a key not found error. We could make a new map where we take an old map and add a little bit of extra data into it. Again, maps are not mutable, so we can only make sort of new names for the new compound map that we've created, right? So M1 plus a new map that we've come up with, we're going to call it M3. We're just giving labels to these sort of deep compound structures. Next up is classes and objects, right? So Scala is first and foremost an object-oriented programming language. So everything's an object, integers are objects. This gives us all of these useful functions like toInt, toString. Those are all member functions of the int object and the string object. So how do we define these? Well, the syntax is pretty straightforward, right? We say class, the name of the class. These are class parameters, which make instantiating the class very easy. It's sort of the user seeable parameters or values that we would want in our class. So in this case, we'll pass in a string and an int. This little commented out section is how you do a constructor in Scala, but we don't actually need to be dealing with that. Typically, the constructors that we'll do, it's enough to just pass in some parameters like this. We could have members of the class, right? So we could have, say, val x, it's a string, which we just add s plus t to. We can have private members of our class. We can have member functions that do something to our class. Again, we end up passing back a unit, which is what happens if we don't have any actual return value going on. And so this will, let's see, that properly compiles, so we have a nice definition of first class. And then if we want to make a new first class, right, we'll typically do a val, and we just call the new keyword here. And then we can pass in the values that we want. So the constructor basically automatically sets up first class with the string being konnichiwa and value 20, and then it will automatically figure out what x is, right? It will instantiate all of these for us. What do we have here? Not enough arguments for the constructor first class. Oh, we have a string and a val. I don't see what, it's this last line here. So you can see that if you don't pass in everything, it'll give you an error. We could do that and that'll still work. So we can call once we make an object, right, an element of our new class, then we could do things like look up its member values like f.x. We can call the member functions by this dot notation. Something to notice here is if it doesn't take in any parameters, right, increment z doesn't actually take any values in, we don't have to put the parentheses on there. We can just leave them out, which is why we see, like with toString, this is actually a function that would normally have parentheses on it, but we just don't need to put it in there because Scala is smart enough to deal with that. In fact, we don't even need to put this in on our definition here, and it will still compile fine. but that sometimes, I don't know, gets confusing. I like to see the def and have the parentheses to at least know that there's no parameters going on there. And then, yeah, let's look a little bit about how to generally turn loops into recursion. Right, so let's see, we have this function, it repeats, we want to repeat stuff k times. It takes in a string and an integer and should return a string. And what's it going to do? I'm going to make an accumulator in my result. Right, this is just the empty string for now. And for each I from 0 to k, I want to add result onto that, or add s onto my result. So I just want to add that string that I've passed in there k times and then return the result. And it just does what you expect. Aussie, we get Aussie, Aussie. Oi, we get oi, oi. Aussie 3, we get Aussie, 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 etc. So how do we do this recursively? Well, right, we can pass in the string and the integer, and if k, the number of times we want to repeat, is less than or equal to 0, then, well, let's just return the empty string. Otherwise, right, what do I want to do? I want to decrement what my for loop is running through, right? So I definitely want to give this k minus 1. And then I also want to add s to whatever this returns, right? So this will keep on expanding outward, and for every one of these calls, I'll get a new s, and I'll end up concatenating those all together. So remember, when you're thinking about recursion, always think about what is my base case, and then what is sort of decrementing or incrementing towards my base case. How am I changing my inputs to make sure that I run into that base case? So this is a straightforward way to do the recursion. Another way to do this is to, right, so this sort of relies on, we'll see next week, we'll talk about recursion and how this is not what's called tail recursive, because this function needs to wait for repeat k times rec to return whatever it returns before adding the string s to it. So it's just sitting there waiting for all of the subcalls to finish before eventually adding s to that return value and passing that back up. Remember, in Scala, we don't actually have to type return. Whatever the last thing in the block of code is what is returned. So we're cool here. But we can do this another way, right? So we can do this where we add an accumulator as one of our parameters, which we'll call a result here. And so what we're doing is, instead of waiting for the return, we say my result, I'm going to hand off my result to the next guy and say what you do whatever you need to do, and then at the end you can return the result. As opposed to me sitting there waiting for repeat k times rec to return and then adding my little addition onto it and then passing it back up to my parent. So instead we say, well, okay, the base case, if k is less than or equal to 0, let's return result. Otherwise, let's repeat k times alt, right, on s, k minus 1, I still want to be decrementing that, but now I want to add s to my end result. Right, so this accumulator is sitting there and it just keeps on adding up everything that I want to eventually return. And now this is what's called tail recursive, right? The final call is just the final statement is just a call to another function. I don't actually have to wait for it to return if I didn't want to. We'll see how this gets optimized under the hood later. But this is a useful way to sort of think about recursion, especially when you have something that you're like a count that you are keeping track of. You pass the count along and you increment the count into those future calls. And so we have this repeat k times alt, and the important part here is that we have to instantiate the accumulator with whatever is sort of the base case is, right? So we're going to do it with an empty string, and that will make sure that, you know, if the string is empty, we'll just return, or k is, say, equal to 0, we'll just return the empty string. And we can double check that this works, and it does. So that's about all I wanted to say about the basics of Scala you need to be able to handle. I recommend looking through the other Jupyter notebooks as well as just playing on your own to sort of get comfortable with how Scala works. That's the only real way to become fluent in the language, is to practice it yourself. But hopefully this gives you a bit of hands-on experience to sort of see how Scala works.